Now, what is specific heat? And that's what we're going to talk about for a few minutes here. Water has a very high specific heat. In fact, it's the second highest of all liquids. And basically, specific heat shows how much heat can be absorbed or released, and it's different for all substances. So I'm going to turn off the PowerPoint. You can get this on Moodle, and I want to talk to you about in a different way. When we talk about specific heat, we're still talking about heat transfer. And now we're comparing the heat transfer of different substances. For instance, I have two metal cylinders here. One is copper and one is aluminum. They transfer heat very differently from each other. And then if we compare it with water, like a bottle of water, water, like I said, has a very, very high specific heat. So what we can do is, using specific heat, we can actually calculate the difference between the heat transfer of substances. On one hand, we can see it qualitatively. You know, we know that water has a very high specific heat. For instance, if you go outside and it's very cold and you have a metal in your hand, very quickly that metal is going to get cold and your hand's going to get really cold. Versus if you go out there with a pot of water and you put your hand in the water, it's going to cool down a lot slower because water has a higher specific heat. Now we can do an experiment for specific heat, and that's why I have this apparatus here. What we would do, and I kind of show you a picture here, I'm going to have a metal like aluminum, okay? And this metal, let's say that weighs about 20 grams. And I'm going to have some water in what's called a calorimeter. Okay, this is a calorimeter, and I just add some water to this calorimeter. And let's say I have 50 grams of water, and it's, we're going to call it at room temperature, it's around 20 degrees Celsius. Now, if I want to compare the specific heat of these substances, I wouldn't want the metals to be at room temperature because then there's no temperature change and I can't really compare. So what I can do is set up an experiment where I actually heat water to its boiling point. And the reason I would do that is because water will stop, the temperature will stay at about 100 degrees. So once it's at 100 degrees, I can add my metal, in this case aluminum, and I could also do the copper. But if I put the aluminum in the boiling water, very quickly that aluminum will become 100 degrees. And then if I had the right equipment, which I could take this then, and I could drop it into the 20-degree water, like this, swirl it around, and take the temperature of that. And what I would find is very simple. Okay? First of all, water would displace. It would go higher, and I've got the cylinder now in there. And it was a hot cylinder. So I know that this is exothermic. The metal will cool down in the water. I also know that the water is endothermic, which means it will heat up in the water. All right? Based on this, I also know that the amount of heat lost equals the amount of heat gained. And I always go this way. You've got heat lost, you've got heat gained put in. If I add the metal to the water will displace a little bit. So now the metal's in the bottom here. Okay? We know the metal's going to lose heat. That's exothermic. If I wanted to calculate the heat of the metal, that would be mc delta T. And it would also be negative because it's exothermic. Now to do the same thing for the water. The water gains heat, so water is endothermic, which again is the same equation, the mass of the water times the specific heat of water times the change in temperature of the water. This is all for the metal, and this is all for water. This would be positive. And I can set those two equal because we know from the law of conservation of matter and energy that the exothermic reaction is going to equal the endothermic reaction. And then I could move these figures around. I can solve for specific heat of water or the specific heat of the metal. If I don't know the temperature of this final system, I could calculate that. Or I could start with the temperature and you can move it around to form different calculations.